Okay, welcome you all for the last section of advanced processor architecture. I'm sure you will all be waiting for it. Okay, today I'm going to cover something discussed about so far. Little bit I touched upon in the early stages, and then I'm going to cover most important concept which all the current processors have. They need to have multi-core processors. That is about cache coherence. So to understand this, you should have an better understanding of cache. So what I will do, I will give a quick overview. Let me do it time so that still we'll get some more people online. Before that, let me complete the context. Then this is very interesting topic. You need to be paying attention closely, otherwise you will miss what is being discussed. But if you understand it, you will know how nicely people have solved this problem in real life. These issues are there and how they are solving it is nice things to know. Okay, so let me proceed. Let us see what all we have done. I am sure you all of you will be able to say what all things are done so far. We have completed all of them to the left. Now what we are going to cover now is about process level parallel architectures, MIMD. Okay, I'm not going to go into the details of how it is implemented and what are the different categories. I can talk for maybe 10 hours, but maybe even more. But I'm going to talk about one key important thing in this talk and finish our discussion about cache coherence. Okay, fine. Now, how we implement a parallel architecture? There are two ways. One is having a shared memory, one single physical shared memory. Of course, we are talking about multiprocessors. Okay, multiprocessors. That means there are multiple processors working together. Whether they all belong to a single CPU. Like if I combine all this, it is nothing but what we discussed yesterday. It is Core i7 quad core multiprocessor. So it doesn't matter whether they are all together in a single chip or in a motherboard. You have bought 3-4 processors and then you have connected them all together, okay, over a bus, and you have a single main memory. So it doesn't matter whether a single CPU with 4 cores is accessing the main memory or different cores which are different chips individually. They are all connected through a bus connecting to main memory and they work together. So it doesn't matter. Our discussion is going to be on what are the issues in running our software on these processors while they are sharing some data between them. Okay, that is our focus of discussion. It could be implemented in many ways. This is one of the way. A symmetric multiprocessor, again, it talks about multiple cores, but whether they all reside in a single chip or on different chips, it's again implementation dependent, but the issues are the same. So what are SMP? I already spoken about this earlier. In a shared memory, this is being shared between multiple cores. And when I say multiple cores, it is default assume that there are processors running in them. Okay, there is OS and there are processors running in these processors. And they have a common address space. You should know what is an address space. Address space is something, either it could be a code or data or stack Okay, stack need not be shared. It is very specific to a particular core or a particular process. So let me talk about core data and core. You have a memory, either you can store code or data, and in physical memory, there will be some addresses. If it has to reside in the memory, and need not be in a contiguous space, it could be split into pages and it may be distributed all through the main memory. We are not talking about any of those memory management issues and how they are split across. Those things are not discussed, because from the process perspective, it is only going to give a logical address. Logical address is a contiguous address. And then memory management comes and translates it to physical memory addresses, and then addresses and access the value stored here. When I say memory management, paging also comes. In that case, though logically they are in a contiguous space on a logical address space, physically they may be on different locations. Even that we are not discussing. It is not of discussion. It doesn't matter whether it is is a virtual addressing is there or not. If it is a directly mapped, doesn't matter. We are going to discuss about the logical addresses, memory addresses that the processor is going to give out. And when it gives out, if I say, suppose a process running in this processor is giving out an address 100. It's a logical address it is giving. It is for the process, the contiguous space is there, and it is trying to access the 100th location in that address space. Similarly, if another process is running, and if I say that they all share the common address space, then if this process is also trying to access an address 100, then both the processes, let's say P1 and P2, have in mind that I am trying to access a location 100, which is mapped to a single location in the physical memory, and that happens to be the same. Remember, that happens to be the same. That means both the P1 and P2 are working on the same common address space. That is, if P1 is accessing an address 100 and another process running on some other core is also accessing the address 100, they really mean accessing a single location where it is mapped to on physical main memory. That means what? Both of them are trying to access the same location, same data. Now, you have learned that processes cannot access the locations of each other. It is protected. Now I am saying a process running on this core and another process running on some other core is accessing a single location in the main memory. Is it not a violation? No, provided it is allowed. The user or the OS, both user with the help of OS, enabled this access. That means there is a shared memory location in the address space of both the processes, which is common to both of them, and they are allowed to access that space. When I say access, I may have different access permissions. I may say that only one of the processes will have a write permission and the rest of all other processes have a read permission. I can fine tune the access permissions using the page table entries, which you are studied in OS. Or I may say it is a common address and both the processes have a write permission. That means both of them can write into it. So it could be configured in any way. I may say that that location is only writable by some process, only by some process, and remaining processes can read from it, but they cannot write. Or I can say more than one process can access a location as well as write into it. I can say that. It is okay. You may ask, why am I doing it? It may be because they are all cooperating processes. They are all cooperating processes. User has split an application into multiple processes and they are all accessing a common data. So they all need to have a read write permission based on the application which is running. Now, what is the job of hardware? As electronics engineers, we need to make sure that what the user wants is provided by the hardware, as well as it is reliably supported. When I say reliably supported, there shouldn't be any wrong values being read by processes, because I am providing a shared access to a particular location. Now, what I mean by wrong values, I will explain. But understand the context, why we want it, and what is that we expect electronics engineers who is designing the processor to support what the application engineers want it from the hardware. Okay, so that's our context of our focus of discussion today. So data movements between the CPUs is achieved through load store instruction. Now I'm going into the processor. It could be a RISC processor. Assume that all of them are RISC based processors. Then they may use only load or store. When I'm saying a memory is being accessed by a processors, multiple processors, they finally access the memory using load or store. Why I am talking about data memory. Remember, our discussion is purely localized to data memory access. Why? Because as far as our discussion goes, we assume code memory is only read only. Only read only. That means what? Even if I have a library, clib, which is loaded onto main memory, which is a shared library. That means what? Processes running on different cores may use the shared library in the main memory. Shared library has both code and data, everything. I am talking about the code of the shared memory. When these processes are accessing the code of a shared library, they are accessing it through program counters. Please remember, each of them are having program counter and they are trying to access the shared library code. They won't use load store for that purpose because only data memory accesses happen through load store. Now, when they use program counters to access the code memory, do they have any requirement to change the code? No, it's only read only. So any number of processors can keep reading this code and start executing them on their cores without having any impact of some other process running the same library, provided this shared library is given access to multiple processes. That OS takes care. We studied about this in our systems programming course. So I am not talking about code access at all. The problem is more or even present only when data memory is accessed. Code memory is only read only. So any number of processes can read them, and they are not going to see a different value when they read the code. They are going to get the same opcode because nobody is changing it. So no issues. Even multiple cores are running them and accessing them parallelly. See, the problem is you have to remember that these processes are running concurrently and they need to access either code or data at a much faster rate to execute the code and perform the data processing. So the problem happens when multiple processors running multiple processes trying to access a common data for either read operation or read write operation. Now, again, if it is only for read operation, assume there are some constants in the data area also, which are only read only. In that case, the problem is not there. Even if it is a data access, if all the processes access them for only read purpose, no issue, because they are going to get the same value which is already preserved on main memory. The problem happens when one of the processes wants to update it and some other process wants to read it. Then are they getting the correct value or not? So that's a problem. Now the problem is more pronounced because of cache coming in between. Now I told you data memory access is a problem because multiple processes concurrently trying to, one fellow will be trying to change it by writing something, another guy will be reading it. Will it get the actual value which has been written by this, or it is going to get a stale value? So those confusion is possible when at least one process wants to write and other processes want to read. This problem is more pronounced. That means it is much more impact when you have a cache in between. Now, you need to understand what is a cache now. Differ for a while, I will discuss about it shortly. Okay. Now, single physical memory, which is shared among processors. And this is called SMP because all the processors are in an equidistance from main memory and they all have an equal time, almost equal time to access them, irrespective of what is the location of the memory and all that, address of the memory. So one simple concept you should remember is in SMP, there is one single physical memory. It is not split into multiple physical memory and located somewhere in different places. It is a single memory, physical memory. Maybe it may have a multiple banks. If you have seen your laptop, you may have a DIMM modules with multiple banks. It is allowed because we don't differentiate to that level. Okay, it is called uniform memory access. That's all. Now let us go further. What about distributed shared memory? This I have explained earlier. Memory, part of the memory could be very close to the processor and some can be they're all distributed with different processes. Assume this way. Okay, I can also have one single another copy of which is common to all. Okay, here I'm not showing that. I'm showing each processor is having some memory which is close to it. Assume that they are all in the same address space. Same address space means, again I explained to you earlier, if this guy is accessing an address 100, maybe this 100 will be in one of the places. It cannot be in multiple places. That address is uniquely, if it is all these processes are on a single address space, it means that if one address is given, that particular byte will be only one copy of it in the whole system. In this case, in a distributed case, it could be located in any of these memories. We don't know. It depends on the configuration. In that case, if this processor is accessing this address 100, it will access it fast. Whereas this guy wants to access it, it has to go through this interconnect and this and access it. So it takes more time. So different locations in the memory have different access time for processors, even in the shared memory case, because it is distributed shared memory. So this is the major difference between an SMP and a distributed shared memory. But the problem that I spoke about, accessing a data which is modified by some process and read by some other process, remains the same. You are having additional load of different access time, but the same issue happens because all these processors are on same address space. Now, what is the, if I say different address spaces, suppose what is the, I will give you one example of that so that you understand it. Suppose if I say these four processors are in one single address space, And these all four processes are on another single address space. Address spaces are different. This is one A, address space A and address space B. In that case, an address generated by this 100 is for this address space, and an address generated by another process 100 is for this address space. So this 100 could be anywhere here. This 100 could be anywhere here. There is nothing called unique location. They are different address spaces. So within the address space, the addresses are unique, not across the address space. You may have a different value, different copy. It may not even exist. There is an idea of address spaces. So alternative design approach is a distributed memory. We are talking about a single address space with multiple cores. Either memory is distributed or it is in a single physical location. We are going to discuss about problem of having a shared data between them, between the cooperating processor. So as I was telling you, there is a shared data which is being accessed by processes running on them, and they need to access it for both read or write purposes. In both SMP or DSM, communication among threads, it could be processes, occurs through a shared address space. Okay, only problem happens when there is a shared address space, meaning that a memory reference can be made by any processor to any memory location, assuming it has a correct access rights. I already talked about this. So there is a common address space, they are trying to access it. All the problem happens because of the shared address space, otherwise there are no issues. If it is a clusters of computers or network of processors, there is no issue. In fact, we are all now connected on network. We are all running Zoom. We are all seeing the same content, but I am not accessing directly anything from here to your memory, though I have an impact on what is stored in your main memory, because what I show you here on the screen is what is there on the Zoom's applications data area, which is it is trying to display from network. It is trying to access it. It would have copied it on the main memory and then displaying it, okay, as an image. But I'm not directly having a control of accessing it direct, changing the value or something. So they are all different address spaces. Your Zoom applications are running on different address space, because where you store a particular data in your laptop is different from what my Zoom is storing in my laptop. We are all not running on the same address space, though application is same. They are distributed and running on different processors. So do not get confused. Anything that is communicating over network will have this issue. No, it is the problem only when they have a common address space. That means the address that I generate is same as address that your processor, other processor generates. They all refer to the same location, then there is an issue. Okay. So in our case, if it is a network of processor, we do message passing. We exchange it through packets. Now we are using the network packets to exchange data. So we are not accessing it directly. Though all the processors on your laptop and my laptop, they are all running the same Zoom application. It is actually running with the browser's help, but there is a application running in your core processor. Now, there are two things like private or shared data. So we have multiple caches, and now the problem I will talk about, because you are supposed to know a lot about cache than what you know right now. So at least little bit I will share it with you, so that later on when you do it yourself, learn, or you are suddenly put into some course which expects you to know cache, you will not have difficulty. Okay. So you have multiple levels of cache trying to access a single location in the main memory. They all go through a shared bus. Okay, there is a bus which is being accessed by multiple cores. So if a bus bandwidth is some 16 gigabytes per second, it is being shared by multiple cores. So it will be a more issue, it will be a bigger issue if suppose it is for the same location. then this memory controller, which is there trying to provide access to the memory, will not allow you to access the same location by two different processes at the same time, because it's going to create a problem. So it will give a delay. It will make sure that there is a delay in accessing them. Because of that, what happens is, if shared data is there, it is going to take more time to access it. Okay, that's what I'm trying to say. So now I told you that processes may have a shared data, or it could also have a private data. The problem is more pronounced only in shared data. If suppose there is a private data, that means a process running here is having a private data which is in the stack, maybe a local variable, or it is only accessible to this own process. Then these processes, there is no need for them to access it. Though the copy of that will be here, they won't be trying to access it. Only one process will be accessing it, one processor, and one process in it. So there is no issue. If it is a private data, no issue. Only if it is a shared data, there is a problem. So private data are used for single processor, while shared data is with multiple processors. You can easily make out that you are sharing means you are sharing with multiple processors. So requirement for shared data arises because of cooperating processes. I told you this, and running on multiple cores. So when a private data item is cache, now I'm going to talk about cache. So let me explain a little bit about cache now, so that you are all prepared to listen to it, whether you like it or not, or you don't want to listen, that's okay. I will explain the cache concept, because without that you will not be able to understand the remaining thing. So there is a main memory. It's a processor is accessing the main memory with the help of a cache. In between there is a cache. Now initially cache is empty. Okay, assume it is some instruction or data cache, doesn't matter, the philosophy is same. So assume some cache, let me say only data cache. Now I have told you that cache has a cache block or cache line. It's a block of data. It could be 32 bytes or 64 bytes or 128 bytes, whatever. So assume that initially the processor wants to access some address 0. It is not in the cache. It is a cache miss. So it goes to the memory, tries to access the location 0. Now assume that the block size of the cache is 32 bytes. Now the processor wants to read only 1 byte, which is at the location 0. It is not in the cache right now, it is here. So when it is trying to access this data 0, the means 0th address, 1 byte, it doesn't get only the 0th byte, it gets 32 bytes from the memory. It gets always equivalent to the cache line or cache block size. It also has this 0, that address 0 also. It brings it and puts it somewhere. It could put anywhere in the cache line. Okay. If it is all empty, maybe it will be mapped to the first location, or it could be anywhere. Then that 0th location is given to the processor. Whatever is the content of that is given to the processor. Now assume that it is a character array. You are trying to write a character array. You access the first location, which happens to be in the address 0. Now in a for loop, you will access character 1, next element. Now it is going to say that I want to access the address 1. That byte is not going to come from here now. It is going to come from the cache. Imagine you are accessing the character array of 0 and writing a value of maybe ASCII of A. That A is going to be written here. It's not going to be written here, because cache copy is there and the processor is going to only do all the operations with the cache. Why? It is much faster, it is closer to the processor, and accessing a cache memory is much faster than accessing from main memory. So it will do all the jobs with the cache, provided it is in the cache. That block of that data is in the cache. So it is writing a, it will be written here, and then it goes on accessing it till character array 0 to 31. 31 is 32 bytes. You know, cache size is, block size is 32 bytes. It will access all these 32 values from cache only, and they would have updated the some data into them. Now it is trying to access cache character array 32. Suppose now it will see that there is a miss. So first location 0, there was a miss, and then remaining accesses are all hit. And when it is trying to access the next byte 32, which is a 33rd element, which is not in the cache, so it will be a miss. Now it will be in the contiguous space in the main memory. It will bring that, and it doesn't have to keep it in the contiguous space. It will bring it and put it anywhere, whichever cache block is free. It will copy that remaining 32 bytes. Then from here onwards, 32, 33, 34, all of them happen here only. Now, let me explain some more about cache now so that you understand remaining things easier. This is whatever number of cache blocks that you can store in a cache is limited because it's a smaller memory. This is in terms of megabytes, this will be in kilobytes. So imagine your processor is accessing very more often, and then all the cache blocks are full. Now it wants another location in main memory which needs to be brought into the cache. There is no space. Now what should it do? It was doing all the updates only in the cache. Right now the contents of the cache and the main memory are different. They are not same. They need to be same, because later on when another process or the same processor wants to access it, it should get it from the main memory without losing the data. Now I told you that it is trying to access some another block and the cache is full. That means all of them are filled with some block. Now what it should do, it should write back and empty the cache, bring a new block there. Now while emptying it, I mentioned it, dirty flag will be set. If any one data in a block is modified, there is a dirty flag which is set in the cache, then it will know that it has modified what it has brought from the main memory. That means the copy in the main memory and the cache are different. In that case, it has to write back that value. Suppose if it has brought something and it has not modified, both main memory copy and cache blocks are same, it doesn't have to write back into the main memory. It can just say that I am going to have this block now in the cache. So this writing back is one way of making sure that main memory copy and cache copies are same. So write back is one policy. That means what? We are not writing back into the main memory every time. We write it only when we want to evict or remove one block from the cache line and to bring something else into the place. This is called write back. This is called write back policy. Write it back only when you need to remove the cache block from the cache. The block means only that 32 bytes. There is another policy called write through. Write through means whenever the processor is changing it here, it also makes sure that it is reflected in main memory, maybe with some delay, but it makes sure that more or less they are up to date. That is called write through. That means the read accesses will happen without any much of delay because it doesn't have to go to the main memory, but write accesses will have to go to the main memory anyway. So it is not getting benefit of performing the write operation without going to the main memory, even though it has a cache. So write through policy is whatever you make change in cache, make sure that you change it in the main memory also. So what is the advantage of write through? in our case, if multiple processors are there, they will see a consistent value on the main memory because the copy is always matching. Whatever is there in the cache block of one processor is same as what is there in the main memory. So if another processor is accessing the same location, they will have its own cache and they will have a copy. It will read a proper value from the main memory. So this is a very important thing you should learn and you should know. Cache, how is it going to impact our day-to-day life in the execution of processes on a multi-core processor? I hope this is clear. Write back and write through, and cache having a copy of the whole block, and then whenever it is supposed to evict, it is going to write back. In the write back case, write through case, it will be updating it. So I am not going to talk more about cache now onwards because you are supposed to know this. Okay. So private data are used for single processor. I told you this. Okay, this I wanted to explain you what is cached. So if a private data item is cached, its content is migrated to the cache because from main memory, reducing the average access time. So you don't need to go to the main memory for every access. So you don't use the bus, common bus. Because no other processor uses the data, the program behavior is identical to the kind of uniprocessor. So let me explain what I mean by that. Suppose if I have a private data, I can bring it to my own cache and then start using it. It doesn't matter whether I am running this process in a multi-core environment or a single uniprocessor environment, because it's anyway private data. Whether I keep it in my own local cache or from main memory, doesn't matter. They don't need it, so it doesn't have a problem. Okay. So now shared data, what is the issue? When the shared data are cached, the shared value may be replicated in multiple caches. Okay. Suppose I am using a shared data on by this processor also and this processor also. A copy of it is going to be here. The same copy of it is going to be here. Multiple copies are going to be maintained in the cache. And they are all going to be accessed simultaneously by multiple processors. If it is for only read purpose, no issue. They are all having multiple copies, but only reading it, no issues. They will read faster, that's all. But if they write, there is an issue. In addition to the reduction in access time, because cache access is faster, bandwidth is reduced, the main memory bandwidth, and contention for accessing is not there because you are going to have a in your own copy here. So caching of shared data is a problem. That is called cache coherence. If suppose I have a data which is shared between two processors, that means two processors running on them, two threads running on each processors, they access the same shared data. That means they have a same copy here. Then what happens? That is what we are trying to address it now, which is called cache coherence. Coherence means, if you have heard about laser beam is nothing but a coherent light waves combined and in phase with each of them. So its power is more. That is called coherence. In this case, cache coherence means you have multiple copies on different caches on processors. They all should see the same thing. They all should have the same value. Just because you have multiple copies, you should not have an issue. So that is called cache coherence. So let me give an example in a banking system. Suppose I am accessing my account from my mobile app and I have given the credentials to my wife and she is accessing it from a laptop. We should not see different balance in the bank. We should get the same value which is in the bank. If I am taking out some money, it should get reflected immediately when other person is seeing it. So that is called coherence. When multiple people are accessing same single data, they should see the same thing on all their systems. So let me give an example. I have a variable x which is having a value v0, and it is being shared between two processors. Initial is v0. CPU 0 reads it. Now what happens? As I told you, it will get a copy of it and then it will be in this cache, a different location in the cache. Okay. Now assume CPU 1 writes a new value v1 into x. Similarly, this CPU also has taken a data, the same data, and it is trying to write it. So, okay, one more thing I will tell you. Okay, some question, I don't know, something is coming. Okay, so what I meant by a shared copy means, see, remember one thing, cache memory is a temporary memory locations. They don't have their own address. When cache is accessed, which is meant to access this location, suppose this is in address 1000, okay, and the processor is accessing 1000. Now, if suppose this data is in a first cache block, then this first block address now, right now it will be 1000. For a moment it will be 1000. So this copy is actually, this is a master copy which is in the main memory, is copied into another memory which is a cache memory. It is another physical memory, okay, but it's a cache memory. That means that block of data which is in the main memory is copied into that location. During that time, cache controller has the information that it is holding the block of data starting from 1000 in a particular location in the cache. So whenever 1000 is given by the CPU, it will know that I am holding this 1000 now, so it will give out the value from here. Now imagine a situation wherein after some time that same location is having a data belonging to 2000. Some data is here which is come to the cache. Now if the CPU is saying I want to access 2000, it will give it from this location because now it is holding the contents of this in this cache. So it is like a scratch pad, temporary memory. It may hold any value of the main memory at a particular point in time. So you can have a particular location in cache mapped to any one of the blocks addresses in the main memory. You cannot say that I am holding 1000 also in the same block and 2000 also in the same block. No, that is physically one block of memory in the cache. It can either hold a value from address 1000 or maybe from address 2000. So don't think also that address 1000 will always come to that particular location in the cache. It may reside for some time, it may reside in the first block. Maybe after a few accesses, it may be mapped to some last location in the cache. You need to understand about cache accesses, two-way, multi-way, four-way, direct mapped cache, all those things. I'm not going into the details of them, which you are supposed to know. But it's fine. Right now, understand the concept that cache is a temporary scratch pad which is holding a copy of it. So it is another copy. Remember, it's another copy. It's not that some mapping is done that it is still getting it from here, and no, it is actually the same content is stored there in another memory. The kind of memory is different. This is a SRAM memory and this is main memory is a DRAM. That is different, but they store values. I hope it is clear. Okay, now when I suppose, if I understand correctly your question, if I say this is copied on multiple caches, they are having their own copies physically present on multiple caches. They are not having it, they are not accessing it here. Okay, they have their own cache, they copy it on their own temporary copy and access it. If let me see. Okay, they access their own cache. There are some facilities that it can get something from other cache, but not directly. The CPU, when it is trying to access it, it is accessing its own cache. And if it is not trying to access this address, it will be stored here. Okay. It won't be from here. Don't think that this copy can be only in one place. It can be on multiple places, on multiple caches. It depends on whether these processors are interested in accessing that memory. That's all. So they maintain different copies and they work with them. So that's the problem. We have a single location are copied onto multiple places. So you need to maintain coherency or consistency between the values of these copies. You are maintaining multiple copies. How do you maintain it? That's the issue that we are trying to address now. So I hope this is clear. Next, when CPU 0 tries to read the value, suppose it has changed it. Now, what it has done, it tried to access the same location and modified it. But it is modified in its own copy. As I told you, cache back means it will be updated on main memory only, sorry, write back means it will write into main memory only when this particular block is evicted. Till then, it will maintain it there only. That means this x is equal to v1 is not going to be reflected on main memory. It is still updated here. This guy doesn't even know, and even main memory doesn't know. It is not having the value. v1 is changed only in the local copy of this CPU 1. Now, if this guy is accessing it, what will it read? It has got its own local copy v0, so it will read v0. But I told you that this is a shared data. That means any changes done by any processor should be reflected on all the copies. If I don't have it, I am going to erroneously read a value which is not even correct, because this value now at this moment it is changed to v1. After that time, after this is modified, if this CPU tries to read that location, it should see v1. It should not see v0. Even though you have multiple copies, something has to be done by the processor system designer to take care of it. That's what I told you. ECE guys need to take care of what CSE want. CSE doesn't care about these things. They said that I want a shared memory. Both processors are going to share it. And their OS came in between. It ran on 2 different cores. And the ECE guys built multiple cores and they provided cache because they want to run the processor very fast. So they brought cache inside. They copied the data and then they were feeding the CPU much easier, faster. They did it for their own comfort. Now, because of that, they cannot say, hey, CSE guys, because I am having a cache now, so whatever value one processor is running or changing, I cannot reflect it. I'm sorry. Then your CPU will not be sold in the market. They will throw it in the dustbin. Now, how do you address it? You have to address it. We did it for some good purpose. We are doing it for process to run faster, but at the same time, it should not cause any issue. Just because I am speeding up, I cannot say that correctness is not guaranteed. You have to speed up, correctness has to be guaranteed. As I told you, the same philosophy. Even in superscalar, we started running all instructions in parallel. Okay, that is for a good intent, but correctness has to be assured. ROB came, you solved the problem. Now cache coherence, we are going to solve the problem. Okay, though we have multiple copies we maintain, we want to make sure that this CPU, when it reads it, some magic should happen that it reads v1. Okay. Now, what are the conditions you are supposed to take care? Let me talk about it. When you have a shared data, okay, and I say that the memory system is coherent, then it is supposed to take care of the following. A write immediately followed by a read to the same location by the same processor should always get the newly written value. Okay, very simple this is. This can be guaranteed because a write, I am writing some value. After some time, I am saying I want to read that value. Because I am maintaining it in the local cache, I will make sure that the new value is written, no problem. When this same address I am reading back, I will give back the same value. If it is happening on the same processor, I can give it, no problem, no issues. Now, a read from P2, a read happening from P2 following a write. That means which is happening first? Write is happening first. Write is happening first, followed by a read from P2 to a same location. Now, imagine you split it into two actions. At time T, this is happening at T1, T2. At time T1, this write happens. Assume the cache is not having it, so it has brought it, the whole block here, and then it will write the value into the cache, a new value into the cache. But this main memory is having the old value. Remember, I am assuming write back. It is not updated every time, right? It is not write through. It's a write back policy. So once it is writing the value, it is only reflected here. It is not reflected in the main memory. Now followed by a read operation to the same location by another processor. What it will do? It doesn't have it in the cache, assume. It goes to the main memory. It will go to the main memory now. Okay, I have not talked about cache coherence at all. So they don't talk to each other. They don't exchange anything right now. Please remember, they don't even talk to each other, these caches. So it goes to the same memory and takes the old value and then gives it to the processor, which is wrong. So what I am saying is, if I am saying I am supporting cache coherence, a read from P2 immediately following a write from P1 should get the latest value written by P1. Even if I do within the same next clock cycle, after this write, I should get back somehow a new value, which is written by this guy. It is currently here only. It is not even in main memory, but somehow you should implement cache coherence that it happens. We are going to discuss about how it is going to be done in the class. Okay. So this is one of the conditions. I should satisfy this condition. Now, this is most important thing, which most of the time people forget it. It's not well documented also. Two writes to the same location. That means two processes are writing to the same location at some point in time, T1, T2. Okay. By any two processes. Suppose P1 and P2 are doing it. Imagine there is one guy. Don't think that multi-core processor means only two are there. There may be n number of processors. So there is another guy, processor, is also having a cache. Its job is to keep reading a location. Assume that all of them are accessing the same location. Now this guy is writing it. So it has brought it here. It has written it. It has written a data, maybe what it has written is D1, data D1. After time T2, this guy is writing a data D2, different data. As I explained to you, both of them will write in their D1 and D2 in their own local copies. They won't do it here without cache coherence. At this moment, imagine processor PX tries to access it at this time Tx, this same location for a read purpose. What should it get? It should get D1. And it accesses at Ty at this time. After T2, it is again reading the data. Remember, when it is reading, it is having its own local copy. Now it is conveniently, it can give it from the local copy, but it doesn't even know that other copy of the same data in another cache is modified to D2 now. So I need to take care using this cache coherence that at Ty, if Px is accessing the same location, you should not see D1, you should see D2. The same sequence in which the writes have happened to the same location should be seen by other processors. Do you understand? The same sequence you should see. You should not see write D2 first and then D1 next. No, because D1 was written first, D2 was written next, it should see the same sequence. Two writes to the same location by any two processors are seen in the same order by all processors on reading the same location. It is not only for PX, it is for true for PY, PZ, any processor. So if I say my processor supports cache coherence, it means I take care of all of them. Just to tell you, yesterday what we saw, Core i7 or any processor that you have in the market, they support cache coherence. If it is a multi-core processor or a processor is supposed to work with multiple cores, they need to take care of cache coherence. Either in the system level or at the processor level, cache coherence has to be taken care of. It is implicit and important. So we need to make sure. How do we do? I will only explain one protocol, maybe two protocol will be too much for you. I understand it's a last class, I agree. But at least if I teach you one protocol, you can read yourself if you are interested. I hope you will. So this ensures a shared location will not have different values. Okay. So a shared location will have different values and it is consistent with the processors. Okay. Now I understood, I told you about what is it supposed to take care. Now these cache memories are introducing the problem now. Actually, imagine a situation where cache was not there. All the processors every time was reading from main memory. Only issue is you have to take care that main memory controller sequentialize the reads. Suppose this is writing first, it should write the value into the memory, and somebody reading it after this time, it should give the data. Then it is writing, it should write the value, and another one is reading the same data, it should give something. As long as the reads and writes are sequentially granted, the main memory controller can take care of it. Though there will be some delay in accessing it, all that. But we have decided that we will not do this because every time coming to main memory is going to be nightmare. I told you our pipeline will not work. I told you the pipeline works because of cache. Otherwise, whatever you do inside the processor is a waste. So I need to have a cache as well as I need to take care of these issues. That is why the cache coherence problem has to be resolved in the hardware. So consistency has to be maintained, and the problems may happen because of three reasons. Because this cache coherence problem, I told you that we have to use the cache. There is no other way. But if I use the cache, it's a problem. Now, where do I have a problem? Only if I have a writable data. I told you code, I can have multiple copies, read only, no issues. But if there is a writable data, I have an issue if it is on multiple caches. Another one, I will not go into the detail, process migration. That means for a time a process is running in a core and then later on they are migrated to some other process. So when they migrate, it is scheduling, okay, context switch happens, and then next time OS is scheduling the same process to another processor. It is called process migration. What happens is, while this process was running earlier, it was using the cache, both code and data. So some entries would have been created in the cache, something would have been pre-fetched and kept. They will all be there in the cache, and you can actually, if it is a read only and the value are still valid, next time when the process is coming and running on the same core, they can take it from cache only. They don't have to go to main memory if it is a read only data. So if you migrate the process to some other core, then you have an issue because you have to afresh read everything now, because the process is coming to the processor newly and it has to read all the code, data, stack, everything from the main memory into the cache and then feed it to the processor. So it's more time consuming. That's why I told you yesterday, CPU ID is there in each core, which is used by the OS to schedule the same process on the same core, okay, if possible, in a multi-core system, so that this cache, the process migration will have a lesser impact. Lesser impact, it's not guaranteed, but lesser impact. Okay. IO activity is also an issue. This also I discussed about this in computer organization course, DMA, direct memory access. Let me just quickly tell you what it is. Suppose if you are getting some data from the network, it has to be copied to the main memory before the protocol stack running on the processor can read it. Now, to read the data from the network interface and complete TCP IP packet to read, it takes a lot of time. We don't need to initiate the interaction from the processor for every data movement. So what is done is the data movement happens directly from IO to main memory. The processor programs it and then leaves it. DMA takes care of it. And then once the complete data packet is copied, then it is informing the processor that you can read it from here. Okay, that is called DMA. When this is also there, you have another IO processor accessing the data, and apart from these processors, so the issue is much more. Okay, parallel access is happening to the same location. So what is the time? Let me break it after this. And the new I'm having a protocol, which cache coherence protocol, will start it after this. So types of data causing less or more problem with coherence. It may cause a less problem or more problem based on the following conditions. If it is a read-only data, no issue. Okay, no problem with coherence. I have told many times. If it is a private writable, readable, it is only a private copy, though it is readable and writable. If it is a private copy, again, no problem. Only if there is a migration, you need to take care of some performance issue. But there is no cache coherence problem. Okay, because only this processor is going to access it. No other processor is going to access it. It's a private data, whether readable or writable, doesn't matter. It can do anything as long as another processor is not accessing it. The problem happens only when you have a private writable. One more, okay, I'll tell you, private writable and shared readable. Okay, here only one person is going to change it, but multiple people are going to read it. Shared readable, private writable. Here what happens? It's problematic. Little, it's okay, not too much, but it is the problem. It's not, you cannot say no problem, because whatever is written by private should be seen by others, as I told you. But if only one processor is going to write and remaining all going to read it, this issue is there, but still it's manageable. Problem is too much only when the variable is shared writable and readable. That means any processor can write into it, any other processor can read from it. Both. This is most problematic because anybody can read it and write it simultaneously, and you will have a problem because consistency is not maintained. So we are going to address these issues. Now, what are the possible solutions? There are hardware solution, software solution. We are going to talk about only hardware solution. Okay, it is a complex solution. I'm going to explain only a simple protocol. Software-based solution is there, but there are some restrictions there, because if suppose I'll tell you what is not cacheable, there is something called, once you identify a particular data in the main memory that is going to be written by somebody and read by many, or multiple people are going to write and read, you can say that this is not cacheable. That means this particular data cannot be moved into the cache. Every time if you want to access it, you have to come to the main memory only. That is called not cacheable. You can make it not cached. That is possible actually. You can configure it. But it's a compromise, but you have an issue here. What is the issue? Every time when you want to read or write from the data, you have to come to the main memory, which is very time consuming. Performance will be impacted. Your pipeline will not run properly. Your superscalar will not run properly. All that problem will happen. Okay. So it's not a solution. So no software solution will hold suitable. When you have faster access you want, you need cache. If you have cache, then you cannot use it the software based. So software based is not a good solution. We need a hardware based solution to be implemented so that all the issues that you have seen can be resolved. So there are protocols there. I'm going to discuss only one protocol today. I will break it before starting the protocol. So there are how they keep coherence. The protocol means there is some way of doing things between a local copy and main memory. Okay. So let me stop here because I need some concentration for you from your side, not from my side, because you are looking at the. Okay, guys, shall we start? Okay. So I will not take much time. I will give you an overview so that you are well prepared to read on your own later on. Because it's an advanced processor architecture course, and if I have not talked about multi-core, is incomplete. And I got delayed because I couldn't go faster. I hope you understand. I understand your feeling also. So one good news, today's class is not there for the exam. Today's class is not there for the exam. It's only for your knowledge. Okay. So listen with a relaxed mind. I don't want to force you. Okay. So we said a processor is accessing it, a main memory, and then there is a cache. So there are different policies based on what they try to do. Policy means some way of doing things, okay? Not insurance policy. It is, this is the possible options I have and I want to do in all of them, okay? First, memory update policy. What I mean by that, I will come to that. And cache coherence policy. Last thing is about how they work, okay? This is about how they work. Now let me talk about what is memory update policy. All of you know that I have taken a copy of main memory into the cache and the processor is going to change it. Now what should it do? Should it write back immediately? Sorry, write through immediately or write back only when it is to be removed? That means you keep updating it here and then write it only when it is supposed to be, the copy is supposed to be removed from there. That is that decision, whether you want to, how you want to make sure the data which is here and the data which is the master copy is here, a temporary copy is maintained here, the processor is updating it. What should I do? Should I write everything that I write it here also, or should I defer it till when I want to remove this copy permanently? That is one decision, which is a memory update policy. When should I update the memory? Other one is cache coherence policy. That is, if I have a shared data where multiple copies of the same data is there on multiple caches, how do I manage it that all the processors see the same data? That is about coherency among the caches. It has nothing to do with the copy of main memory. I worry about only what is there in the cache. That is called cache coherency policy. And protocol type is how do I implement the cache coherence? What type of protocol I use to make sure of this is taken care of. I hope this is clear. So let me explain to you. There are so many things are there. I wanted to cover only these through. This not going to be covered. Don't worry about this. I will come and show you what they are. Okay. Each one I will explain with an example. You will understand all of them. Only thing you should know that memory update policy is about between a memory copy and a local copies. This is the master copy. These are all local copies. What do I do with this between these two? It talks about that. This is talks about several copies I am maintaining in the cache. How do I make sure that they are all synchronized? Okay. So this is about hardware implementation. I am not going into that. So let us see. Memory update policy, there are only two, very simple. Write back, which I explained already when I was explaining the cache. If I have to update a new value, store D1 in my local copy, okay, I will not update the main memory. Main memory is not shown here. Oh, sorry, it is here. Main memory is also shown. I have changed the value, the same location is there in all the places. Okay. Previous value was D in them. D is a value. And I am updating, this processor is updating with a new value D dash. Now, this is still D. It is not making sure that this copy is updated, because memory update policy worries about only between these two. It doesn't care about this. So its thinking is only what should I do? If it is having one copy here, it means it is certainly going to be in main memory. Inclusion principle. It may be in other cache or not, we don't know. If the same data is being accessed by other processor, it will be there. Otherwise, it may not be there. So this policy is only talking about these two. What should I do if I am modifying my own local copy? Should I take care that I modify this also, or I defer it till I remove this entry from here? So in this case, I am deferring it. This is called write back policy of cache. Another one is write through. Go through that. If I am having a copy here, I'm sure it is there in the main memory also. If I am updating it here, I will make sure that the main memory, the master copy is also updated. But I don't care if it is there in another cache. I don't care about whether it is updated or not. In fact, it is not updated. As far as this policy goes, it is only worried about my cache data with the data in the main memory, whether they are, what am I doing with that? So I will take care of that updation. So this particular policy only worries about this. That's all. Okay. So I hope this is understood. So cache coherency will take care of this. Okay. That is a different policy. So let me explain it with what is it actually. Write back policy. That means what? If I have a copy here, I have a master copy here, I will only change it here. I don't bother about this. That is called write back. So it is a lazy policy. That means it is not going to come to the main memory every time to update it. It is lazy. It will only update it in the main cache and doesn't bother about main memory until that particular block has to be removed, so that it will write back and then remove it if it is a dirty bit is set. So what are the issues? Data in memory is updated only at some events. What are the events? When a data is replaced or invalidated in the cache. When I say that a particular data is no longer valid, or I am saying that it has to be replaced with something else, then only I will update the main memory. Otherwise, I will keep updating it only in my local copy. I don't comment that. So this is a lazy policy. It has a temporary incoherence. Temporary incoherence means for some time, what is here and what is here are different. And if this value is there in another cache also, it will be different. So you are not guaranteeing 100% coherence at all the time. While not updated, suppose this is not updated, read references to memory will be redirected to the appropriate cache which is holding the updated value. So let me explain what I mean by that. Someone asked the question whether this cache will be talking to this cache or not. It will. In this case, what we will do is, suppose you have updated the value here, but you are not updated it here because you are following a lazy policy, then you can implement it that if it is updated and this value is no longer a valid value, if this processor is accessing the same location, it will not go to the main memory. It will take it from the cache, which is having the updated value. It will take it from the neighbor. It need not be neighbor. It can be some other processor. It will take it. Okay. Don't worry. It is one way of solving it. Now, what is the issue with this? Needs more complex cache controller. Each cache is having a controller. It will be complex because it is supposed to either read from here or read from the another cache which is having that particular location contents. So it has to know which cache is having it, whether it is updated or not, and then take it from there. So remember one thing here, the negative aspect. If it is request is coming from the another cache, this cache is supposed to give it. Remember, it is not a request coming from the CPU. Cache is only supposed to take care of the request coming from the CPU. But here, this cache controller is supposed to take care a request from another cache. Same thing is true here also. This cache also should take care. Some other cache can come and ask for it. So cache controller becomes complex because it is supposed to take care of the request from CPU as well as from other caches in the system. And if you have too many processors, there will have too many cache and there will be total confusion and it is difficult to implement. So it's one problem with that. Another category is write through. I explained that a greedy policy. It's not lazy. Every time it updates it, it updates the main memory also. That means it is not getting the benefit of having a copy here. Only read will happen from here, but every write has to go to the main memory. So its performance wise is very less, what you gain from it. So what is the negative aspect? Imagine a situation wherein only this process is using it, okay? Even though it's a shared data, it's not that always all the processors need to use it. It may not use it for some time, it may use it for some particular time and then stop using it later. So a shared data, just because it's a shared data, somebody else can read from it, you are doing too much of writing into it every time, which is a greedy policy, and it actually creates more traffic in the interconnect between the memory and the CPU. So that is a negative aspect of that. But it is more reliable. That is a positive aspect of it. So this is not a simple bullet, negative aspect and positive aspect. So what are the cache coherence policies? I will explain this only one of them so that you will understand it. And rest of it, I will leave it to you to read yourself at your leisure. So let me explain what it is, okay? So there are, write update cache coherence policy. Remember, it is nothing to do with the memory and the cache copy. It is between the cache copies, okay? Between multiple cache copies, not between the main memory and cache copy. That is a different policy we have seen. That is write through and write back is between the cache copy and the main memory, whereas cache coherence policies are between multiple copies of the cache. So there are two types again. A write update policy. That means if suppose a processor is writing a new data into a location, if the same block is there on multiple caches, suppose they have also taken it from the main memory and they are having it, then this policy takes care of updating in all of them. How it is done? Hardware. There are some separate buses are there. It will take care of it. It is called write update. Okay. While writing, make sure that if you have multiple copies in other caches, make sure you update them also. Now, what is the advantage? Everybody gets the new value. As I told you, what are the conditions of cache coherence is taken care of here. Anybody doing a write is reflected on all the caches, so it's good. No incomplete data, inconsistent data. Right. Another one is write invalidate. See, it is like this. Suppose imagine a situation where only this processor is writing it, updating it continuously. But these processors, they have a copy because they wanted it and they brought a copy. But currently the code is somewhere else and it is accessing something else, and they are not using this actively. They are not using it actively. It depends on the program flow, where it is right now. What are we doing? Even though these processors are not using the data consistent now, just because they are having a copy of it, we make sure that every time I update, every write I do, I update everywhere. But these guys don't need it. They don't want it. Now it's a waste of traffic on the bus, time and effort. So what do I do? But at the same time, I cannot compromise on the cache coherency. Simple thing is, if I am writing the data and the same block is available on other caches, I don't care whether they are using it currently or not using it. I go and invalidate that entries. That means what? I forcibly make them invalid. That means if by chance these processors want to access the memory, the same location, it will see that that is invalid now. Whatever old stale copies were there, it is invalidated. Now what they can do, either take it from the main memory, in that case this will be updated and taken, or this cache will be seeing it. Okay, if suppose somebody else is wanting it, then it can provide that to it. Wow, okay, you need it now, you take it now. Okay, that is possible. Multiple caches can communicate with each other on a different bus, not on the main bus, which is connecting the main memory and this processor. They caches are connected through different bus and they communicate among themselves. Yeah, do you have a copy? I want it now. Do you have you updated it? Yes. Okay, you take it. So the request can come from another cache and it can provide it. It is based on need. So what you gain, only those processors who are interested in accessing it are given the updated value. The rest of the processors do not use it, do not need it. They are invalidated and they don't even know because they are not accessing it. So it's okay. If you can understand this, what happens during the cache interactions and how they are connected, actually you are in a better position to learn on your own when you want to understand this. Okay, these are all the issues which need to be handled, and there is a lot of hardware things done underneath. Okay, so this is called write invalidate. When I am writing it, if there are multiple copies, I invalidate it. One more thing, this policy only talks about between caches what I do. Now during this time, this cache may have the memory update policy as either write back or write through. It may have any one of them configured like that. In that case, if it was write back, this value is updated only here and main memory copy is still old value. If it is write through, it would have been updated here also. At the same time, it is invalidated here. Remember that. So write back and write through are only between what I do. If I change my copy that I have brought from the main memory, if I make a change, will I reflect it on the main memory or not? That is decided by this policy. I can configure the cache to do one of this. Similarly, during the same time, parallelly, I can have a cache coherence policy, which could be either I do this or I do this between them. So there are two different things I do based on what I am supposed to do based on the configuration, either by hardware done by the user or by the manufacturer. Okay. So I hope this is clear to you. Now I will explain with the words. Write update is a greedy policy. That means you are updating on every cache entries. So all the local copies are updated immediately. Copy in the main memory may or may not be updated based on this. Okay, it depends on that policy. It doesn't guarantee that if I'm updating on other cache copies, I will update in main memory. No, it depends on this policy. Okay, so immediate data migration. I am doing a data migration immediately. I may be generating unnecessary traffic because of this, if it is infrequently used data by other processes. So this I explained to you already. This is the negative aspect. And another one is cache controller have to accept a write request, not only coming from the processor, also from other cache controllers. Whoever is updating it, they will inform the other guys. So if this is updating it, it will inform everyone. If this is updating it, it will inform these two. So it is like you can imagine the complexity. Okay, how many such occasions may happen, but still all of them will have a consistent copy. Okay, and I hope this is clear. Now write invalidate. It's a lazy policy. I don't want to pass the data. I'm very lazy to send the data. I only inform them that I have changed it now. You make your entries invalid. And if you want it, come to me, I will give you later. Okay. So a data is updated on local copy and other copies are invalidated. So same thing other processors will do. But if it is invalid, it cannot do. First, it has to take the new value. And then if it is updating it, it will take the new value from here and it will update it to D2 and it will make this invalid. So the same thing will happen, because if all of them are, they need to have the same policy. Okay, that is one more important thing. In a system, you cannot have this fellow following a write update and another guy following a write invalidate. No, they all need to talk same language. So they all need to have the same policy, either memory update policy or cache coherence policy. They need to have same, so that they are consistent across them. So this is called a lazy policy, right? So let me write while not updated in main memory. See, it could be again main memory may not be updated. It depends on again whether you are having a write back or whatever. So if write back is there, it will not be updated. Data is provided by the updating processor cache for the read request. See, imagine a situation. Okay, let me explain what it is before I want you to think. The policies of memory update and cache coherence are independent. You can have 4 combinations. One, both write invalidate and write back, write update and write back. All combination I can have. 4 combinations I can have. If suppose I have chosen write invalidate for cache coherency and write back for memory update. Okay, that means what? If I am updating here, I am not going to update the main memory. Then who is having the latest value? The owner of the data. So that cache only will have the data. So in that case, I cannot prevent anybody asking for the same location. So as I explained just now, if this processor wants to read it, suppose, it will say, I want to read from this address. Now, this cache controller will be snooping the address bus, which is being accessed by all these processors. They will be looking at the address bus. And if anybody is interested for the same location which is held by this processor, it knows I am having a write back policy and main memory does not have the actual data. I am having it. So I should provide it to the person who is asking for it. So it will put the data into the bus. So it can be the same address data bus or different bus. These control buses are different. Okay, these control signals are separate, whereas the data movement is through a normal address data bus. So each cache controller not only looking at the processor and receiving requests from there, it is also snooping. Snooping means just looking at it, what is happening on the bus. If anybody is trying to access the location which I am owning, I am having, and I have modified it, memory will not provide the data. Somehow assume that the protocol takes care of it. This will provide the data because memory is not updated now. It knows that it is in write back policy, so it will take care. So cache controllers have to accept any invalidate command coming from different processors or a read command.